Yeah, welcome to the session this morning, oral session, Fingerprint and Security. Let me introduce myself. My name is Christoph Busch, representing Gjøvik University College in Norway. We have 4 distinguished speakers here in this session this morning. And you all learned yesterday at the dinner and the banquet dinner that our ICB 2015 will be in Phuket in Thailand. So our first speaker is a very distinguished speaker because he's one of the co-chairs of ICB 2015, but that will be not the topic of his talk. The topic of his talk is fingerprint quality assessment using frequency and orientation subbands of block-based Fourier transform. Would you please go ahead?
Yes, thank you, Christoph. My name is Wutipong Arikun, and from Department of Electrical Engineering, Kasetsart University, Bangkok, Thailand. I will present my student paper. His name is Grisada Promsutirak. He is here, and if I need any assistance from him, if you ask me some difficult question, probably I have to ask him. Okay. So this is my outline of my talk. It's introduction, proposed method, experimental results, conclusion, and future research. So introduction. In general, fingerprint may contain defects. Following factor. First, user character. Second, sensor characteristics. Third, user behavior. And fourth, environment. The FX performance will be affected by this effect. So we need to be very carefully to assess the quality fingerprint to improve the performance of the FX. Okay, this is a literature reviews. So existing fingerprint quality assessment method can be classified into 2 types. One is a direct method and the other one is transform method. Direct method try to capture the feature directly from an image and then convert into some quality measure. For example, directional fields, reach frequency, and pixel intensity. These are the 3 features that most people use. And then there are some combination that from, for example, NFIQs. So they use all of these to make some quality measure. On the other hand, transform method. We have a Fourier transform, Gabor, or anything. This is the way that we transform the image into any other representation or any other domain. And then we try to convert coefficient information in that domain into some quality measure. So these are the list. Fourier transform, Gabor filter, symmetric representation, and gradient PDF, and as well as PCA. So my proposed method is in the first one, the Fourier transform. So the problem, the existing problem. First, most methods rely on orientation field, which may be unreliable due to the high curvature and noise. And the second, most methods fail to evaluate the quality around the singular point area. Third, quality measure of the elastic distortion and insufficient area is still a challenging problem. And the fourth, how can we assess the quality of latent properly? So at this point, we attack the first and the second, not the third and the fourth, because it's still in the dark, and we try to find the light from that. Okay, the proposed quality assessment method. So this is the block diagram of our proposed method. First, we have a fingerprint, then we partition it into the blocks, and then we do the overlap block-based Fourier transform. And then you got the frequency, you got the Fourier coefficient, and then you rearrange it into frequency subband and orientation subband. And then from the subband, this subband, you can analyze the quality from this subband into the global spectrum quality, relative spectrum density quality, and relative spectrum orientation continuity quality. These are the 3 main feature that we extract from this subband, and we combine it into total quality of the fingerprints. Okay, overlap block-based Fourier transform. Actually, as you know, probably it's called short-term Fourier transform. But for me, for us, it's no time, so we prefer to call it overlap block-based Fourier transform. Basically, the block size is smaller than the window size. When you partition it, it's small one, and then when you take Fourier, you take larger than that. That's all the concept. And this is the key of our research. So once you break into the block, and then you take Fourier transform, you have the both spatial domain and frequency domain. This is a 4-dimensional signal. So 2 in spatial and 2 in frequency, right? And then if you group the same coefficients together, for example, the red one grouped into the same group, now we build up the subband. And each subband represents the same as spatial domain and frequency domain, but in some other way that we can easier to extract the feature. So the goal to do this is to exploit fingerprint feature in both spatial and frequency domain. So let me show you the subband. Okay, the left side, can I have pointer? Okay, and the left side is original, and then you have overlap block-based. Thank you. Overlap block-based Fourier transform. And then once you group it into the subband, you can see that for each particular subband, this is represent one frequency and one orientation of the whole image. Okay, one frequency and one orientation of the whole image. Okay, next. Now this is 4-dimensional. We try to reduce into 3-dimensional signal. So we can find that frequency subband representation. So we integrate frequency, the same frequency together to get the subband. So the frequency is depend on how far you from the center to outside. So this is a circular integration. So you get the first, second, third subband and so on until this is a 0 frequency until the highest one. So actually the frequency of the fingerprint is around here, but you can see that there are strong spectrum about the edge or boundary of the fingerprint is somewhere in low frequency. Okay, next. The orientation field. The orientation subband representation. Instead of integrate the frequency, integrate with the orientation. So we try to integrate in some direction that we get some from 0 to 180 degrees. So each subband represents one orientation. Now you can see that this is a 3-dimensional signal. Okay, next. What we do is we try to filtering, or we use the frequency markings to mark out the boundary of the fingerprints. So this is before the masking, without the masking, and then after the mask, you can see that we remove some boundary spectrum out of this subband. Okay, you can see this. This is because it's 3-dimensional. The time is orientation. Okay, now this is moving. If you move into the subband in 3-dimensional, you can see that we change the orientation. Okay, now I want you to see this. Okay, for the low quality one, you can see that for high quality, this is what is the rich the spectrum still packing, very dense. But for the low quality, the spectrum dispersed. So this is the way that we can measuring the quality. Okay. So we propose 3 new quality assessments based on rich frequency subband and rich orientation subband. The first one is global spectrum quality. The second one is relative spectrum density quality. And the third one is relative spectrum orientation continuity quality. Okay, for each one, I'll explain in detail. The first one, global spectrum quality, we just integrate it all from 3-dimensional to 2-dimensional. So that's all the spectrum of the rich are packed into just one image. So this is all. The second one, we use the passing window to measure how rich spectrum compact. So you have a window, you have just like a 3D, the sphere, and then if the energy in this sphere are packed and large, we got the strength of the rich spectrum. So This is the image that we got. You can see that in this location, the energy is not packed. But we go through with the Paschen window in through the subband, we get this image. Okay, the third one. The third one we call relative spectrum orientation continuity quality. We track the strong rich spectrum to find the rich continuity. What we do, we select the starting node with the highest, probably this one. Okay. For each any location x, y, we find the highest spectrum. And then we start it from there. If the orientation is still continuing in this way, we follow. If they switch into the other subband, we're going through it. So as long as the string go, the highest quality is it. Okay? So this is the image of the third one. Now we combine all three together. So this is the first quality, this is the second quality, this is the third quality. And then all fingerprint quality is come to this image. Let me show you. Okay, performance evaluation. We evaluate by measuring verification accuracy, EER, of the reject low quality image. For each fingerprint quality assessment method, we choose the worst quality image by fixing the same rejection fraction of all images in each database. For example, if you have FVC 2004, you have 800 images. Then if I said we're going to reject 5%, 40 images will be thrown out. So each algorithm will select the worst 40 images and throw away. The rest going to verification by WOSOT 3 with minutia detection package, NIST biometric image software. Then we compare all the algorithm with the OCL, orientation certainty level, Gabor, local clarity score, frequency domain analysis, as well as the NFIQ. Okay, this is, I try to show you the location as well as the strong or the more lighter is mean the good quality, okay? And the darker is lower quality. So each algorithm gives us some number and we try to show that this is the results. Okay, one good point I have to show you is about this. The singular points. We have not effect. Unlike the other algorithm, probably they have effect around the singular point area. So this is the one of the advantage of this algorithm that we do. Okay, for the worst quality. Okay, for the graph. So we plot the equal error rate with the fraction rejection. For the FVC 2004 DB3, this is a fingerprint from thermal sensor. It's doing good, the lowest one. And then we test with FVC 2006 DB3 as well, they are still low one. But for the optical sensor, it's not that good, it's still above the NIFQ. But anyway, we still have room to improve because NIFQ using neural network as well as all of the feature, but we use not all of that, still have room to improve. About the computational complexity comparison, this is a roughly comparison, not seriously because we implement all the code is not optimized, but we implement all the code except NFIQs with original paper with C++ language. Okay, conclusion and future research. We introduced the new quality assessment method based on risk spectrum in spatial and frequency domain. The advantage of our algorithm is to assess quality directly from risk spectrum. So no need for the orientation estimation, no suffering caused by incorrect directional field. The second is be able to separate between singular point area with good quality against the low quality area. It works best with the strong risk spectrum such as fingerprint from thermal sensor, but disadvantage is we still have a work marginal with the fingerprint from optical and capacitive sensor with low signal to noise ratio. So we show you the picture that why our algorithm fail. You see that the risk in the thermal sensor is very distinctive. Let's say that the frequency domain is very strong, spectrum is high, but in here you can see the broken risk. And the broken risk lower the spectrum. Then we have a problem that we can separate the spectrum of risk and the noise is more difficult. Capacitive one is the worst. Okay, this is one thing that I want to point out that we're doing research on latent fingerprint enhancement. And the good one require progressive enhancement. What do you mean? What I mean by progressive enhancement? The progressive enhancement doing that you select the best quality to doing enhance first. And once you finish that, you feed the information into the lower quality and do it again repeatedly. Let me show you the algorithm that we developed called adaptive boost spectrum filtering. This one, in short, is ABS. So this is the image. You see that we start from the good quality, get into the lower quality and lower quality, get inside that. Okay. So this is the one way that we attack the latent enhancement problem. And okay, further that, we test with some of the forensics problem. This is a latent with some letter or insights. And then, first of all, we didn't directly use the ABS, but we do some bandpass filter, Gaussian bandpass filter, to boost some of the rich frequency. And then after that, we can apply the ABS. Actually, the ABS, you have to read the paper that they saw everything is in fingerprint, so they make it fingerprint rich. Okay. Then the future research, how can we assess the quality of the latent properly? This latent fingerprint is by Royal Thai Police and Central Institute of Forensic Science in Thailand. So they are very dirty and there's a lot of many finger in one. So we got a lot of research problem from here. And then we connect with the New South Wales Police, Australia, and we got very challenging image in here. You see that? The top one, this is a fingerprint on your clothes, on the fabric. And this one is a fingerprint behind the net. And the fingerprint with some, very, noisy for my point of view. Okay, I think that's all for my talk. Thank you for your attention, and please welcome to the ICB 2015. We will be the host, and we welcome you all to Phuket, Thailand. Thank you very much.
Yeah, thank you, Wutifong, for the presentation. Maybe to put some framework around this contribution, you may know that ISO-IEC SC37 Standardization Committee is working on a revision of ISO-IEC 29794-4, which is sample quality metric for fingerprint image data. And Wutifong indicated in the discussion before this talk that he would like to contribute to that standard. That standard is open for comments, open for contributions. And if I may start with a question, Wutifong, you know that by experience results differ from database to database. You have shown good, impressive ERC curves on the FEC. Did you test other databases, and are you willing to test on the operational database that NIST is providing for the ISO project?
You mean in NIST something like that? Because only we have is FEC and NIST. That's all.
Yeah.
You mean that NIST one?
Yeah, obviously the operational data from NIST cannot be released, cannot be put to the publish. Okay. But in such a situation, algorithms have to travel to the confidential database or to the.
Okay, I will be happy to do that. Any questions?
Further questions from user?
slides, you have mentioned that the singularity points are really problematic for quality assessments. However, it wasn't very clear to me how you could avoid them, given that you are not doing any extraction of them explicitly, or did I misunderstand you?
Okay, the point is in here. I think we combine all these three together. Okay, why it's work? Okay, look at the first one. The first one is called global quality. So the global quality integrates all of the risk frequency. So in the center, the frequency is still there. You see that the frequency they integrate, but they with the several subbands. But if you see only one orientation, you see that one strong spectrum. But in the singular point, they are all in many. But when we integrate it, so they pack into information that we can show that this is a good quality or this is a bad quality. Sir.
Yes, but it is impossible to see the singularity points from the spectrum that you are extracting.
Yeah.
That's my major problem. We published a work back in 2007 on how to first extract these areas and then add the quality of these separately. Because if you make an orientation estimation in these areas, you will have more than one orientation at the same time. You cannot escape this problem in this block decomposition either. You still have the same problem in my view.
I'm not sure that because we didn't extract the orientation, the gradient, something like that, because we go into frequency domain. Once we go in frequency domain, this is something like we have at least 3 ridges or more than that to get the spectrum.
But you are integrating along a single direction. You discretize your directions, right? Each time you integrate along one direction, you are de facto doing orientation estimation. You're not escaping it. You're just doing it in a different way. You are doing it in the Fourier domain, in my opinion.
I'm not sure, but I need to discuss with you. I'm not sure that I get your okay.
Thank you.
But I will see you, sir.
I suggest you take this point later for a consensus-building discussion. Okay, thank you very much for the question and the discussion. We proceed to the second contribution in this session. We stick actually with the topic of fingerprint sample quality. Wutipong already indicated in his future research the relevance of sample quality metric for latent fingerprint images. The second presentation is from Michigan State University, presented by Sunfrey Aurora, feedback paradigm for latent fingerprint matching.
Okay. Hi everyone, I'm Sanpreet from Department of Computer Science and Engineering, Michigan State University, and I'll be presenting our research on latent fingerprint matching. So first of all, just to emphasize why this problem is really important. Latent fingerprints have been an important source of forensic evidence for identifying suspects for like over 100 years. So besides solving the active crimes, they have been used to solve passive crimes. Now, what do I mean by passive crimes? Here is an example. For example, this crime was conducted in 1969 in Houston, and the technology was not so advanced at that time. So the FBI continues to open the old file cases and use their IFS to try to find the suspect. Now, here is a suspect which was recently found who had committed the crime in 1969. And this got the FBI Latent Hit of the Year Award 2011. The other importance is, of course, that FBI continues to, has a goal to improve latent fingerprint matching, and the Next Generation Identification Program lists latent fingerprint matching as one of its major goals. So continuing with the motivation, why do I want to work on this problem? I think this was very well emphasized by Dr. Jain in his keynote speech on the first day. The best matcher in the NIST fingerprint evaluation 2003 achieved like a 99.4% accuracy on plane prints, but the ELFT EFS report, which was released by NIST in 2012, has only 63.4% accuracy in the lights out mode. So there is a lot of scope to improve latent fingerprint matching as compared to the full fingerprint matching. So this gives me a lot of motivation to actually drive my PhD work towards this problem. Let's see some of the challenges in latent fingerprint matching. To the left, you can see an image which absolutely has poor rich clarity. You are not able to see the rich valley patterns very clearly. So, I mean, it's really difficult to match such kind of images. The next image is an image which has a very small friction ridge area. So, I mean, again, it's a very big challenge to match such images. But the most complex thing I would say is the complex background noise, the image to the right, which has such a difficult background that it's really difficult to match the image. So these are some of the challenging aspects of the problem. Now I would go to explain what are the existing solutions for the problem. The existing solutions essentially are based on the bottom-up matching paradigm, as I may say. So the latent matchers existing in the literature are essentially doing this. They take a latent probe image and they first pre-process it. So basically the pre-processing module contains both segmentation and enhancement. The next step is the feature extraction after pre-processing. And finally, you match the latent to the exemplar background database, which already has extracted features from the exemplar, and you generate a match score. So this is the bottom-up data flow, as we may say. Now, the problem with such approaches is that the feature extraction for latents is not reliable. So that means in the bottom-up paradigm, every module has to work sufficiently well for the whole pipeline to work. So if the feature extraction module doesn't work well here because of the poor rich clarity and the background noise present in the latent, the pipeline is not so efficient. So what do we propose now to improve the pipeline? So we propose to incorporate top-down information or feedback from exemplars. So what do I mean by that? Is that while matching the latent to the exemplar, we can refine the features of the latent using feedback from the exemplar. So this is done on the fly, basically. Now I will go ahead and explain how we apply this proposed paradigm to the problem of latent fingerprint matching. So we basically resort the candidate list generated by a bottom-up latent matcher. So how is it done? This is basically the overall idea. You have a latent image. You get the initial feature set in the bottom-up mode. You use the bottom-up latent matcher, generate an initial match score, and a candidate list, which is basically the top K candidates. From each candidate, you can take feedback to refine the features of the latent. So basically, this is done for each latent exemplar pair while matching them. And you can use the refined feature set to match the latent in the top-down mode and generate a new match score. Now finally, you can fuse the two match scores to generate an updated match score and use this to resort the candidate list. So this is the whole idea of the proposed algorithm. Now there are basically 4 different steps. These are listed here. I'll go in detail one by one and explain you how essentially this is done. So the first step basically is called initial matching and alignment. So this is essentially just matching the latent using a bottom-up latent matcher and generating an initial match score and the matched minutiae. Now the matched minutiae generated by the latent matcher in the bottom-up mode are used to align the latent and exemplar pair. And this is essentially the very first step, very simple. So the next step is extracting exemplar features. So this can be done, I mean this generally is already being done in the matcher, so I don't really add on anything onto the matcher. So you have an exemplar image, you can get the skeleton of the image using a commercial system, and you can get the block by block orientation field of the exemplar. So this is a very simple step. This is mostly the commercial systems have the exemplar orientation computed in them. Now, let's go to the third step, which is the crucial step, I would say. It is called latent feature extraction. How do we extract the latent feature? So basically, we do it in the Fourier domain. Again, we go local in every block in the latent. We extract a subimage, smooth it using a Gaussian mask, get the weighted image, then get the magnitude spectrum in the Fourier domain, take the peak points, top 4 or 5 highest magnitude, amplitude peak points, and then get the orientation levels corresponding to those peak points. So these are, So here there are like 4 orientation levels, top 4 orientation levels shown. So this gives us a set of candidate orientations in each block. Okay, now how do we do feedback here? It's really simple. Basically for each overlapping block between the exemplar orientation and the latent, which is basically determined using during the alignment step, you can take feedback. So how do we take feedback? So here is in yellow is shown the exemplar orientation in this particular block, and these are the 4 possible candidate orientation for the latent. So basically we just pick the closest orientation of the latent in that particular block, and this is selected just using the orientation difference. And so basically we get a refined latent feature set using this mechanism in every block. And similarly, we refine the latent frequency. The refined latent frequency is just the corresponding frequency to the selected orientation level here. Okay, the final step basically comprises how do we compute the feedback similarity. Now, there could be various functions, but we just go with the simplistic. So this is basically just computing the difference in the orientation fields. Delta theta is the alignment angle between the orientation fields. This is the refined latent orientation and the exemplar orientation, and this is a normalization constant. So you just use the exponential distribution, and over each block, each overlapping block, you sum up them and divide them. So this is just the idea of computing the similarity, orientation similarity. And similarly for frequency, you can compute the difference, the absolute difference in the frequency, and use the exponential distribution again and generate a frequency similarity. So the final step basically is how to update the match scores. This basically involves, you have an initial match score which was generated by the bottom-up latent matcher. Now you can get a new feedback orientation similarity and the frequency similarity. So we just use product fusion to fuse the match scores of the matcher and generate an updated match score. Now why do we use product fusion? Because we are using like exponential, so if we use exponential and we product them, so essentially, it turns into a sum rule, which gives you the highest, best possible updation in the match score. So now this was the overall approach. Now, of course, the question is, how well does it work? So let's first look at the NIST-27 database, which is the only publicly available database for latents. There are 258 operational latents. I tried to wrap the paradigm around a recent latent matcher which has been recently published in TIFFs. And the background consists of about 32,000 exemplars. So the dark blue curve shown here is the baseline matcher, which is the matcher in this paper. And if I wrap the matcher using the ridge orientation and frequency feedback, as you can clearly see, I get a huge increase in the rank 1 identification accuracy. So again, I want to emphasize that these are operational cases, so the paradigm does work. Now, I also tried to run the experiments on another database which was collected at the West Virginia University. And again, the same latent matcher, I wrapped the paradigm around that matcher. The background consists of 32,000 exemplars, and the rank 1 identification accuracy here improves by 3%. This is because these latents are not actually operational latents, so they do not exhibit the true characteristics of latents. Most of them come close to rather good quality fingerprints. So the paradigm doesn't really help that much, but still there is subtle improvement in the accuracy. Okay, so here I show some successful cases using the feedback paradigm. Now, we applied the paradigm to resort a candidate list of 200 candidates, top 200 candidates of the bottom-up latent matcher. Now, if I include the top-down data flow for that latent matcher, for this particular print, the rank improves from 92 to 5 after feedback. And shown here is the extracted orientation field in blue. In red is the ground truth orientation field. So this is the initially extracted orientation field in blue. So as you can see, there are regions here where the initially extracted orientation field is not close to the ground truth orientation. But if you refine the orientation field on the fly using feedback, you get a good refinement and it gets closer to the ground truth. So in a way that improves the latent feature and further improves the accuracy. Another case right here. Here, look at this region again. not very good initially extracted orientation field, but if you refine it using feedback, you get it very close to the ground truth. So for this latent, which was initially extracted, initially the true mated exemplar was retrieved at rank 42. Now we are able to retrieve it at rank 2. So this clearly shows that the paradigm works. However, as you may say, that nothing is perfect. So let's look at a failure example and why it fails in some cases. So there may be cases where the rich structure of the imposter is very similar to the mated exemplar. Now, since we are only working with level 1 features of orientation and frequency, so for this particular case here, the imposter exemplar has very similar structure to the mated exemplar, and the refined orientation field is exceptionally good. So for this particular latent shown here, the mated exemplar rank degrades from about 6 to 27 after feedback. So the primary reason is, as I mentioned earlier, the rich structure is very similar, plus the mated exemplar is of poor quality. So these are the regions these are the cases when actually the paradigm fails. Okay. So finally, to conclude my presentation, I'll just want to summarize the whole thing. The first important point to note is that the feature extraction from latents is really challenging, as I showed in some of the earlier examples. The rich clarity, this is probably because there is poor rich clarity and there is complex background noise. So what do we do to handle it? We incorporate feedback from exemplars to refine latent features, and this improves the accuracy. Now, the experimental results we have conducted using a baseline latent matcher on 2 different databases with a good background size, it shows that the feedback paradigm works sufficiently good. Now, the other important point to note is that this is just a generic paradigm. I wrapped it around a latent matcher. Now, this can be wrapped around any latent matcher to improve its matching accuracy. Of course, we need to know the underlying algorithm for that. So it can be integrated while designing the latent matcher into the latent matcher to improve the accuracy. Now, some of the future work is, of course, currently there are cases where even feedback from the imposter results in improvement in the rank, for the imposter exemplar. So we need to design the similarity computation in a better way. And the other thing is we can include additional features. Currently, we just work with the orientation and frequency features. We may try to include level 2 features like minutia in the future. Thanks a lot.
Thank you for the presentation. Are there questions?
I'm wondering how you can avoid the problem of the so-called confirmation bias. So let's say at the first stage, the initial thing, you have a wrong match at top 1, and then you are trying to improve the latent features based on that match, then you are kind of increasing the likelihood of the match for that particular print, right?
Mm-hmm. So the idea here is basically that if you are taking feedback from the true mated exemplar, then it leads to a better refinement of features to that exemplar than compared to the other imposter exemplars. That is why the paradigm essentially fails when the imposter is of really good quality, and its rich structure is really similar to the mated exemplar. So that is the idea.
What's the impact of this algorithm on the efficiency of the algorithm?
So currently we have implemented the algorithm in MATLAB, and it takes about 4 seconds for a query to resort the candidate list. So I'm sure if we implement it in C, we'll be able to further improve the time. But I don't think for latents, I think time is not of too much of value. I think accuracy is really important. So the accuracy gain is really sizable here. So we should go and use use the paradigm.
And do you assume the mated fingerprint exists in the template? Is it a condition that...
So we only apply the paradigm to resort the candidate list of the top 200 candidate exemplars returned by a bottom-up latent matcher. So if the mated exemplar is not in the top 200, we are not essentially going to get it using the top-down matching. We are just trying to improve, just trying to push the rank further using the top-down matching paradigm. That's the whole idea. So if it's not in the top 200, we can't essentially handle that case.
Another question.
Okay.
What's the value of K, the candidate list?
It's currently we are doing for 200 candidates. Now it was again determined because I think it was mentioned in one of the keynotes earlier that latent matcher ideally works really good for 70% of the prints, or the 30% are really at the last. So you can't essentially handle the cases which are really at the last using this. It's only focusing on the initial part and just improving the rank further. That's the whole idea.
Okay, I will discuss you.
Okay, sure.
With you later.
Sure, we can discuss offline.
Good. It's time to proceed. Thank you again for the discussion. We are proceeding to face recognition. The title of the third presentation is Poisoning Attacks to Compromise Face Template. This is work from the University of Calgary in Italy, and the presenter will be Fabio Roli.
Thanks. If you open, yeah, thanks. Okay. On the screen, can you do it large? As view. Full screen mode. Okay, thank you. Good morning, everybody. Let me immediately start with one relevant concept that is also provide us the motivation for our work, for the work that I'm going to present. The concept is template self-update in face verification system. I imagine that all of you know well how a face verification system is working. You usually have a template database containing one or more templates for each person, and then you have a matching algorithm. And usually in a verification setting, when the comparison of the matching algorithm of the input image with the template is higher than a verification threshold, the input image is considered genuine, and so the identity is verified. This is the normal operation. But some of the verification systems are equipped with a functionality that is called template self-update. It's a simple functionality, but it's quite useful if you have a changing environment. For example, when the appearance of people, of course, can change, or the environmental condition can change. Template self-update works quite easily, because if the input image, the matching score of the input image is not only higher than the verification threshold, but it's also higher than a more conservative threshold called update threshold, you can use the input image to update your template, the template that you are using for that client that is submitting the image. Of course, you use a very conservative threshold because you want to be sure that you don't update the template using an impostor. And this is the basic mechanism that is called template self-update. You can also, and of course this is the mechanism. You can also take a look of the operation of this template self-update mechanism in an abstract feature space where your template can be represented at a single sample so a sort of centroid, and this is the current template. When you receive as input an image that is quite close to your current template, and so this image can satisfy what I call the update threshold, the update similarity threshold, because the image is for sure a genuine one. You are recognizing it with high reliability. You can use this image to update your current template. Of course, now I'm considering just one template per person, but you can generalize this to a gallery of template per person. And in this geometric setting, when you self-update the template, of course you can imagine that you use a sort of averaging between the two images, the old template, the current template that becomes the old, and the image that you are using for self-updating the template. So in a geometric setting, you can imagine that you are moving your template, and the update corresponds to a movement, to a shift in the feature space of the template. Well, you can use different policy to update your template in this self-update setting. Usually people, they use the last 5 or 10 in general images that have satisfied this update condition, and so they are with high confidence genuine image to update the template. Self-update, it's easy to understand that can be useful to improve your templates, and so you are able to track some changes. Suppose that these changes are quite slow, and you can track them. But unfortunately, in addition to being useful to update the template to improve the performance, it can cause a problem, a security problem. That is the key message of my talk. The problem is due to the fact that you can imagine that a malicious attacker that is aware that your system, your verification system, is using template self-update could exploit template self-update, and so could try to submit a sequence of images carefully fabricated, carefully designed, just to move your templates toward his template, the template of the attacker, and so compromising your template. Or in the worst case that I will show you can happen, can really substitute your template. So this is what I call a poisoning attack. And in a previous work with some colleagues, we have shown that this poisoning attack really works when, it's easy to be implemented if the attacker has a perfect knowledge of the system. A perfect knowledge means that the attacker really knows everything, knows what matching algorithm you are using, which feature you are using. And in this case, in this previous work, we have shown that on average, 20 attack images, so 20 trials of the attacker are enough to substitute completely your template with his template. But about 8 to 10 trials of the attacker are enough to compromise the templates. Compromise means that your template cannot be more used because the false acceptance rate becomes too high and the genuine acceptance rate becomes too low. In this talk, in the paper of the proceeding, I tell you that the poisoning attack can also work if the attacker has a limited knowledge of the system. It's not necessary that he knows everything. And it can also work if you are using quite sophisticated matching algorithm, and also if you use more than one template per person, not just one. Also if you use a gallery of templates per person. Well, the starting assumption is about what the attacker knows about the system. This is the starting most relevant assumption for any adversarial problem, what the adversary knows of the system. In this work, we assume that the attacker has a limited knowledge in terms of what he knows of the template. He doesn't know the exact templates that you are using, but he can get some images which are quite similar to your templates. Well, these images could be taken from the website if you make available some images. This is a key assumption, and I want to stress that, because of course we are assuming that the attacker knows something of your appearance, so have at least one image that is quite close to yours, and so it can be used as the first attack image. I will say you something more about this key assumption in my last slide, because it's also one of the limitations. So it's a key assumption and is one of the limitations. But suppose that the attacker has these quite similar images of yours, he can start the attack. And in the paper, we have shown that this attack that we call poisoning attack can be formulated as a minimization problem. Can be formulated as a minimization problem because basically what the attacker wants to do is to find a sequence of attack images which are quite close to his images, the attacker template, but at the same time satisfy these constraints. That mean that should be also quite similar to the template of the victim, so that the system, the face verification system equipped with the template self-update can use them to update the templates. So this is the formulation of the optimal poisoning attack, is a minimization problem with a constraint, and the solution is not difficult. You can find the solution exploiting the Kuhn-Tucker conditions, the same condition that you use for support vector machine. And the solution is a sequence of attack images. And from the geometrical viewpoint, this attack image, if you see them as samples in a feature vector space, they lie on the straight line connecting the initial estimated victim templates, I mean the initial image that the attacker is using as an approximation of your template image, and the attacker template. The goal of the attacker is to substitute your template with his templates. This is the formulation, and in the paper you can find the mathematical detail of the solution, but it's nothing novel. It's something that you can do exploiting the Kuhn-Tucker condition. And what is nice from the theoretical viewpoint is that the solution also progressively reduces the limitation of knowledge that the attacker has about your templates. So while the attack goes on, the attacker knows better and better which template you are using, in the sense that he moves your template, your true template, and it modifies your template, exploiting the operation of template self-update, so that in the end, it's able to move your true template toward his template. And this is the operation of this optimal poisoning attack. And the uncertainty that the attacker has about your true template is reduced more and more. Here you can see just one example of this optimal poisoning attack. This is the sequence of attack images, and these are the templates of the victim that are updated. Initially, of course, the attacker should submit an image quite similar to your template. But at the end of the attack sequence, he can submit just his face without any need of using any fake face. And so at the end, the template of the victim has been substituted completely. And so you don't have anymore your real template, but it's been substituted by the template of the attacker. Well, in the paper, we also have found some bounds about how many attack images the attacker should provide. And we found some bound. And the bounds, of course, depend about how much the face appearance of the attacker is similar to your face appearance, of course. This is a crucial measure. And the other is how many images the template self-update algorithm is using. How many images, for example, are averaged to create the new template. But in any case, you can immediately see that the number of images, the bounds, scale up linearly. So, well, the attack is quite effective. Well, just another concept before moving to the result. Our optimal poisoning attack provides the solutions in terms of a sequence of feature vectors. But indeed, you have to submit images to the face verification system. So you have to map back from the feature vector solutions to the images. This is something that is important. There are some matching algorithms for which this reverse mapping is quite easy. Imagine that you are using principal component, a matching algorithm based on principal component. In this case, mapping back from the feature vector to the image is straightforward. You have just to invert the matrix. But in the general case that you are using more complicated matchers, that use more complicated feature space representation. For example, you are using the elastic bunch graph matching algorithm. In this case, you are not able to map back to reverse the mapping from the feature space to the images. This is a general problem. It's quite well known in machine learning and signal processing. It's called a pre-image problem. But in the paper, we propose a suboptimal solution. When the matching algorithm is too complicated and you are not able to map back from feature vector to images, we use a suboptimal poisoning attack. And basically what we do is searching for attack images directly in the image space, not more in the feature space. And the essential point means that I have 5 minutes? Okay. Thanks. Quite clear. Okay. And it's a linear combination of the template of the attacker and of the template of the victim. Okay. About the experiment, we collected a database in our lab, 40 clients, 60 images for each client, collected in 2 temporal sections. And we use a small set for training, for creating the template, and the majority for testing. Let me show you one paradigmatic example of the result. So for a specific pair of victim and attacker, and when you have, of course, a limited knowledge, the attacker has a limited knowledge. You see here, in this example, the attack images, in this case, 14 trials, and so 14 submission of attack images are enough for the attacker to substitute completely the victim templates with his templates. So at the end, with 14 trials, the attacker has substituted the template of the victim. Here you can see the false acceptance rate and the genuine acceptance rate as soon as while the attack is going on. So, for example, I can highlight that after 4 or 6 attack iteration, the false acceptance rate increases a lot, and the genuine acceptance rate decreases a lot. That means that the template has been compromised, cannot be more used, because the genuine user is not more able to assess the system. His identity is not more verified, and the attacker can assess. It's much more easy for the attacker to assess. Sorry, just to note that I don't show you the other result, but similar result has been obtained for all the other identities in the database. There are some results that I don't have time to show you. One interesting result in the paper is that, of course, the success of the poisoning attack depends on the particular pair of attacker and victim. It's quite intuitive. And we revised the Doddington Zoo to show that. There are lambs and wolves with respect to this attack. And this attack also works for if you use multiple templates per client, not just one. Last slide, I want to stress you the limitation. 2 main limitations of this work. The first is we are assuming that the attacker has an image that is quite similar to the one that you are using as a template. This is a limitation that we are trying to overcome. And the other is that we assume that the attacker can submit the whole sequence of attacks without any genuine access in between. But we are working to devise another algorithm that has not this limitation. Thanks very much for your attention.
Thank you, Fabio. There are other questions?
My question is that why do we need to update the template from uncontrolled environment in the first place?
Yeah. So your question is not about the attack, but about the need of a template update functionality. Is right? Is correct? Yeah. Well, basically, template self-update is used to support. Usually people, they can have some modifications, some changes of their face appearance, and also the environmental condition can change. If these changes over the time are quite slow, you can track them updating your template. Track them in the sense that for sure you need to track them, otherwise your templates become outdated. I'm not sure if, because if your question is...
No, my question is not...
Oh, sorry.
My question is not the need to update the template. The question is the need to update the template from uncontrolled environment.
For uncontrolled environment.
Correct. Why do we need to do this?
Uncontrolled environment? What do you mean exactly with uncontrolled environment?
Because when you enroll the template or update the template, you have to go to the secure physical to a place. Right?
Yeah.
And authenticate with your ID and other things.
Yes.
The enrollment of the template.
No, sorry, but template self-update is not done during the enrollment, but during the operation of the system.
But obviously, we have contradicting assumptions on when to update the reference. I have a bit related question, Fabio. The reference that you estimate where you start from and the pass to the attacker's image, that I can understand that you model that and morph all the intermediate images that you need. But what I cannot anticipate is the system to be not aware of any potential presentation attack. I mean, any of these systems is likely to incorporate of these presentation attack detection mechanisms and identify that what you present as the morphed image, let's call it this way, is actually a fake. I mean, how do you
Yeah, no.
do you anticipate eye blinking and all that stuff? My impression was that these are all still images.
Well, you are definitely right. Well, the question, if I can rephrase, is, but liveness detection can be a good countermeasure against this attack, and the answer is yes. Yeah? And the answer is yes. On the other side, as you know, liveness detection, while in operational environment, is not yet a mature technology, and so not all the system they deploy this. But anyway, the answer is yes.
So obviously there's need for further discussion.
Of course.
Like
Well, definitely yes.
So we're quite progressed in time, so let's thank the speaker again. And we stick with the contribution that is related to security from the Institute for Infocom Research in Singapore. Narakuma is presenting BioSafe, biometrics-based secure authentication and key exchange.
So, good morning, everyone. So this paper is about secure authentication between a client and a remote server across an insecure channel. And then how do you do mutual authentication and key exchange in such a scenario? So we all know that there are several authentication solutions available now, starting from digital certificates, PINs, passwords, two-factor authentication, one-time passwords, and so on. But then all these existing solutions are neither fully secure nor are they convenient to the user. So does adding biometrics to this mix really solve the problem? in my humble opinion, we need to take this step by step. So let's say you have a client and a server. So biometrics is just one part of the solution. It's just authenticating the client. And then you need to have other complementary technologies like cryptography, network security. You need to make sure that the code is running securely. And all these factors are required in order to enable secure communication. But then if you just consider the biometric component alone, even that you need to consider different issues. So how to ensure the liveness of the biometric trait. So we have all seen the spoofing competitions going on at this conference. So how do you ensure the integrity of the feature extractor and the matcher? So that's another issue we need to address. And then how do you do mutual authentication? So biometrics is not going to solve your phishing attacks, which is right now very common in password-based systems. So soon there will be a time when you will be tricked into submitting your biometric to your phishing website. So how do you achieve mutual authentication so that you know that you are interacting with the valid server when you are conducting a transaction? And then there are issues related to template security and preventing abuse of the biometric data. So this is with respect to the privacy of the user. So in this paper, we are addressing the last two questions. So how do you achieve mutual authentication? And then how do you secure the template and protect the privacy of the user? So biometric crypto systems is one of the solutions which have been proposed for template security, which essentially works by usually by binding a cryptographic key with the template and only storing the secure sketch or the secure template in the database, which can be used to recover the original template with another closely matching query. So the problem with this approach is this is just focusing on the client authentication part again. And then most of the existing secure sketch schemes do not directly address the problem of revocability. You usually need to have some kind of external random factors in order to provide the revocability in biometric crypto systems. So several publications have looked into expanding or building upon biometric crypto systems in order to develop a secure authentication protocol. So one such approach is the one proposed by Bowen et al. So here, basically the sketch is stored in the server for each client. Whenever there is an authentication request, the sketch is sent back to the client who uses a new biometric sample in order to recover the embedded key. So basically the K prime is recovered, and then using this K prime, you can encrypt the randomly generated session key and send it to the server. So once the server receives it, it can do the secure communication based on this random session key KR. So this solution actually authenticates both the client and the server. Only the server, the valid server will have your secure sketch or the secure template. So it implicitly authenticates the server too, and it facilitates the exchange of a session key. But then the problem is it solely relies on the strength of the secure sketch approach. So here, if you see in step 2, the secure template is actually sent to the client during every authentication attempt, irrespective of whether it is a genuine user or the imposter. So, yeah, and then it's sent over a, let's say if the channel is insecure, any eavesdropper can have access to this secure sketch. So the problem now comes down to how difficult it is to decode the secure sketch without the biometric data. So it solely depends on the strength of the sketch. And this approach does not address the issue of revocability also. So another protocol which has been proposed is the secure key sharing protocol by Kanade et al. So here the idea is they want to address the revocability issue. So basically they divide the biometric template into several components and then shuffle these components by using a shuffling key. And the client stores this shuffling key. The server just stores the shuffled template. So the claim is that the shuffled template is revocable and secure, which we will show later that it is not so. So basically in this approach, whenever there is an authentication request, the secure sketch or the key binding with the biometric template takes place dynamically. So the session key is randomly generated and then it's bound to the template. And then this secure template is sent to the client who can recover the the session key by using a new biometric sample, the biometric query. Okay, so here the security still depends on the strength of the sketch. So again, T star is being sent in the open to the client. So basically, it boils down to how difficult it is to decode this T star in order to get your biometric or the session key. And really, shuffling does not provide any revocability because it's just shuffling between different components. You can treat it as an unordered set, and then just like you do fingerprint minutiae matching, you can try to find correspondences between the components of two biometric templates. So it basically does not provide any revocability. So before I proceed to explain how we do the secure authentication and key exchange, I just want to give a brief overview of the error correction scheme we are using. So it's basically a two-layered error correction scheme. First layer is you have a polynomial generated from the key, and then you randomly generate some x points, and then evaluate the polynomial at these points. Basically concatenate these x and y values, pass it through a linear error correction encoder in order to get some code words, which is concatenated to get the code word vector. So during decoding, what happens is there is some biometric noise added to this data. The first step is this linear error correction decoder, which basically handles all the random errors within each component, and then the polynomial reconstruction is used to handle the burst errors. And then this results in the regenerated key. Okay, now we proceed to see how the BioSec protocol works. You have a client and the server. The assumption here is that the enrollment is done in a trusted location. So basically, all the templates and all the intermediate data generated during enrollment is not available to anybody else. So it starts off with obtaining a biometric sample and then feature extraction, and then dividing it into different components, just like the approach by Carnade et al., and then shuffling it based on the scrambled template. And then you have the key, which is applied to the error correction encoder to generate the code word. And then there is this server transformation key, which is generated in a pseudo-random fashion. So we put all these things together in order to generate the secure template. So the template consists of the biometric data, the code word obtained from this key, and also this pseudo-random and independent server transformation key. So the client stores this secure template and then some hash values in order to do the verification. The server stores the server transformation key, this KSR, and then again some hash values for verification. So one can see that there is, apart from the secure sketch, you also have this factor server transformation key, so that adds additional security to the template, which is available at the client side. And then it's also provides easy revocability, but just by changing this server transformation key, we can generate revocable templates. So the authentication has a few steps. So basically, it starts off with the authentication request. Then the server authenticates the client, generates a response, which is used to authenticate the server, and then recover the session key, and then you have the session key acknowledgement before the communication starts. So now I will explain the individual steps in more detail. So the client authentication request basically starts off with obtaining the biometric data and doing the same thing, feature extraction, dividing into components, and then shuffling them. And then this is combined with this secure template to generate this quantity Q, which can be encrypted using a public key of the server, along with some nonce information to get the client authentication request. So essentially, if you look at this Q quantity called Q, it's basically the code word plus this server transformation key plus whatever the difference between the two biometric templates, the error. So it does not contain any biometric information as such. So it can be sent over an insecure channel even if there is no public key encryption. So this public key encryption is really optional, which provides an additional layer of protection. So in step 2, the client is being authenticated by the server. So it's again starts off with the decryption of the request, and it's combined with this Q is combined with the server transformation key, and then the error correction decoding is applied to recover the key. And basically the output are the corrected code words and whether the authentication is successful, and then you get the client nonce. So if you look at this Q plus this KSR, it's essentially the code word with some errors, so it can be decoded. And it provides strong client authentication because only if sufficient number of components between CA and CE match, then only you can be able to decode the correct code words and do the successful authentication. In step 3, the server sends an authentication response. So here, this is very much similar to the enrollment by the client. So here, the code words can be considered as some kind of biometric. The corrected code words obtained in the previous step can be considered as some kind of biometric, which is combined with the code word from this randomly generated session key. And then the server transformation key is added. So this U is very similar to the enrollment template which we obtained. And then this can be sent to the client by using a symmetric encryption, the key for which can be the V prime which was obtained in the previous step, or it can be combined with a nonce to generate a one-time key. So how this protocol achieves mutual authentication is because the server which has the server transformation key corresponding to this particular client, only that server can generate a valid response. So without knowing the server transformation key, it is not possible to generate a valid response. So that kind of authenticates the server to the client. And finally, the step 4 is the server authentication. Here you have the decryption. Basically, you combine this Q, which was obtained in step 1, with the U, which is obtained from this authentication response. And then this is used to recover the session key, and then which you can verify whether the authentication is successful. So basically the output is the session key, which can be used to send the acknowledgement in the next steps. So this Q plus U is essentially the code word which was obtained from the session key plus the biometric noise. So it's possible to decode it to get the recover the session key. So this session key exchange will be successful only if both the client and the server are authenticated successfully. So let's look at the security of this proposed protocol. Let's look at it step by step. Let's say there are attacks on the server side. So no biometric data is being stored in the server. So, and even if all the server credentials are compromised, which is basically the transformation key, the private key of the server, and then some hash values, the attacker can at most masquerade as the original server. So it basically it can act as the original server and then fool the client, but it cannot learn any information about the biometric data. On the other hand, if you look at the attacks on the client side, even if all the client credentials are compromised, he can still not masquerade as the original client because he still needs a valid or closely matching biometric query in order to do the authentication. And let's say the client wants to do some funny things. It wants to recover the server transformation key from the secure template, but that is not easy even if you have the original biometric data. You still need to kind of do a brute force guessing of these many bits. Here, basically, L is the degree of the polynomial used in the error correction. N is the number of bits in each component of the template, and D is the number of bits that can be corrected within each component. If we continue the security analysis, what happens if both the client and the server are compromised? So all the credentials are known. So in this case, you end up with the basic secure sketch. You can remove all the other authentication factors, and then you end up with the basic secure sketch, which is still computationally difficult to break. But then this difficulty is much lower than the earlier case because the entropy of each component in the biometric template is much less than the number of bits in the template. And so we can say that the biometric data is as secure as in the protocol 1 from Bowen et al., even under this worst case assumption. And then finally, if there are any attacks on the communication channel, we can see that all the data between the client and the server are encrypted, even though the channel is insecure. So in terms of experiments, Basically, we have conducted experiments on the fingerprint and iris images from these databases, and some of the algorithms are listed here. These are the error rates, false non-match rates for different false match rates. Obviously, one can see that the error rates are quite high, especially in the case of iris. This is mainly due to the suboptimal feature extractors. And this can be seen from what are the false non-match rates even without any template protection. So if you just use the features extracted and then do the matching, still the higher rates are quite high. And then there is only a marginal decrease in the error rates due to the BioSig protocol. So just to see whether there is potential for improvement in the performance, I just ran a few tests in the last couple of weeks. Basically, fingerprint I just replaced with a different minutia extractor and the minutia cylinder code representation. In the case of iris, I just talked to Christian Rakhtab a couple of days back and then downloaded the toolbox and then ran it overnight yesterday. And I noticed that basically the error rates can be decreased significantly by 30 to 50% by using these different feature extractors and representations. So note that I'm just downloading the data and then running the executables directly from all these sources without any parameter tuning or optimization for this particular databases. So if you do those kind of things, it's possible to reduce error rates even further. To summarize, what I have proposed is a new authentication protocol which has the following characteristics. It can securely authenticate the client based on biometrics. It can do mutual authentication between the client and the server. Can facilitate a secure exchange of session keys, and then easy revocability is possible just by changing the server transformation key. So that's it. If you have any questions, I'll be happy to answer.
Maybe two short questions. We have maybe just a clarification. In the enrollment situation, we just discussed this in the previous talk. Is my understanding correct that the enrollment is not in a controlled environment?
It is in a controlled environment.
It is controlled.
Yeah. And basically, in this case, we are assuming a trusted environment so that all the intermediate data generated during enrollment is not available after enrollment.
There's a question?
How does protocol withstand the replay attack and unlimited attack?
Okay, replay attack, basically you need to have the same kind of protection for any biometric authentication. So you have these error rates, right? The errors basically, the E, which I show here. So because of all this shuffling we do, this E is random. So if you observe the same kind of things which are being repeated, this E, you can keep track of the last few authentications in order to detect whether it's a replay attack or not.
Eventually you will submit the Q XOR U, right?
Yeah, so if you submit the same queue every time, it will have the same E. So the server can know that it's basically replay.
If an imposter captured this information you are submitting to the server, for next time you will definitely get access to the server. It's not immune. Did you see what I mean?
No, but then even if you capture the biometric trait, there is inherent variability between different captures of the biometric trait. So you cannot have the same kind of errors every time. So let's say I take a sample now, take a sample tomorrow, there will be some error. But then if I take a sample the day after tomorrow, it will have a different error from what it was from yesterday.
So are you checking this at the server side?
So this can be done. Right now in this protocol I'm not checking it, but that can be easily implemented.
Good. I don't see any further questions. Thank you again for presenting this work. That concludes our first oral session today. Please stay in the room. We continue here with the spotlight poster presentation.